Welcome to today's session on understanding and managing complexity through a deeper look at dependencies. By the end of our time together, you'll understand the crucial difference between syntactic and causal dependencies and be able to apply a formal definition of dependence to real code scenarios. Distinguish between correctness, build, and performance dependencies and make better architectural decisions based on causal impact analysis. We talk about dependencies constantly in software engineering. We discuss things like lower coupling, tighter cohesion, dependency injection, and dependency hell. Yet, despite all this talk, dependence is usually waved around with no precise definition. This creates real problems in how we think about and manage our code bases. There are several reasons why dependency feels fuzzy to most developers. First, we have what linguists call polysemy. The same word describes build links, runtime links, semantic links, and more. When someone says A depends on B, they could mean any number of different relationships. Second, we have a syntactic bias in our tooling. Most dependency analysis tools only look at surface structure, things like imports, method calls, or inheritance hierarchies. They tell us about the syntax of our code, not about the deeper relationships that actually matter. This creates an intuitive versus tooling gap. When developers think about dependencies, they're mentally asking, if I tweak module A, will module B break? But our tooling reports A mentions B somewhere in its code. Now, these are fundamentally different questions. Now, let me give you a concrete example of this problem. Imagine you have a logging statement like logger.log scattered throughout your code base. Your dependency analysis tool will tell you order service depends on logger. But in reality, changing the logger implementation rarely breaks order service. The tool is reporting a syntactic link, but there's no meaningful causal relationships. This is what I call the core problem. Syntactic links are extremely noisy. A logging library, for example, might be depended on by half your code base according to your tools. Yet, it rarely affects correctness when you change its implementation. We need a better way to think about this. Now, let me introduce you to a more precise way of thinking about dependence, based on research by Koppel and Jackson and Halpern Pearl model of actual causation. Here's the formal definition we'll be working with. A depends on B with respect to property P if and only if there exists a reasonable change to B that would alter whether P holds for A. This definition might seem abstract at first, but it's actually very powerful because it has two crucial parameters that make it adaptable to different situations. The first parameter is the property of interest, which we'll call P. This is what outcome we care about. It could be correctness, build success, latency, energy use, or any other measurable property of our system. Think of this as answering the question, will this feature still work versus will it still compile? The second parameter is what we consider reasonable change. This is a set of edits we consider plausible in our context. A teammate refactoring a function body is reasonable, but management suddenly deciding to delete an entire repository is not. These two parameters, the property we care about and the scope of reasonable changes, lets us specialize the same causal framework into many different types of dependence. This is much more useful than the all or nothing approach most tools give us today. Now, let me contrast how the industry currently approaches dependencies with its formal casual view. In the current industry approach, any mention creates a dependency. If module A imports module B, calls a method on module B, or inherits from module B, then A depends on B. Period. This creates dependency diagrams that turn into hairballs, where a logger appears to be critical to everything, and we have no way to distinguish between different types of dependence. The formal causal way is very different. Our relationships, only relationships that can actually change observable properties, survive as true dependencies. This gives us a much cleaner, actionable view where the logger's true impact becomes clear, and different properties create different dependency graphs. Here's what this means in practice. Under the current view, module A depends on logger because it calls logger.log. Under the causal view, module A has no correctness dependence on logger because changing logger's implementation doesn't affect A's business logic. A might have a build dependency. If you delete the logger class entirely, A won't compile. But for most practical changes to logger, A is completely unaffected. This distinction is crucial for making good architectural decisions. Now, let me walk you through three fundamental types of dependence that emerge from this formal framework. The first type is correctness dependence, where the property of interest is whether the program behaves as specified according to its business requirements. Consider this example. We have a payment calculator class with the calculate total method. This method gets a subtotal from an order called discount service.calculate discount to get the discount amount and returns the subtotal minus the discount. Now here's the key insight. Changing discount service.calculate discount can make payment calculator.calculate total return wrong results. If the discount calculation changes, the total calculation changes. This is a genuine correctness dependence because the correctness of one module depends causally on the behavior of the other. The second type is build dependence, where the property of interest is the ability of the system to compile or link successfully. Consider an order service class that calls payment calculator or calculate total to process an order. If we rename the calculate total method to compute total, the order service code will no longer compile. This is a build dependence. Order service needs payment calculator to have the right method signature to build successfully. Importantly, this might be only a build dependence. If we rename the method but kept the behavior identical, order service would still work correctly once we update the method call. The business logic dependence is different from the syntactic dependence. The third type is performance dependence, where the property of interest is response time, throughput, memory usage, or other performance characteristics. Now consider a user repository class that uses a hash map for caching users. If we replace hash map with a tree map, the lookup latency increases because tree map has logarithmic rather than constant time lookups. Any code calling find user experiences this performance change. They now have a performance dependence on the repository's internal data structure. Notice that the correctness might be unchanged. Find user still returns the right user, but the performance characteristics are different.